structures, and then we'll do that. No, tutorial 3. Yes, tutorial 3, question 2. Spend a minute to read the question if you haven't done it already. So in A, they want the maximum bandwidth that may be obtained without equalization if the total capacitance is 6 picofarad. So the bandwidth, the maximum bandwidth, we can obtain without equalization or before equalization is equal to 1, 2, this is a high impedance front end. Okay? So this is how we define the bandwidth. Our total is RB in parallel with RA, and the total capacitance were given as 6 nanofarad or picofarad. So we just substitute the values, and you will get 1.3 13.3 kilohertz. Such a small bandwidth. Okay. So then this is without equalization. In B, they want us to calculate the thermal noise per unit bandwidth. So this is A. They wanted per unit bandwidth, so that's why we didn't multiply by that. 4 by 1.3. Temperature was given at 300 Kelvin, and RTL is 2 mega. And this will give you 8.29 10 to the power 20 minus 27 ampere square per hertz. Okay, in C, they want us to compare the values you obtained in A and B with those that we can obtain from a high input impedance amplifier. So, okay, first, what will be the bandwidth of the charge impedance? The long derivation we had last time. We found that the bandwidth of a transmit. Yeah. And G was the gain of the amplifier. Over which arm? We have here the feedback, yes, RF. And RF was given as 100 kilo ohm, and the gain was so if you do the calculations, you will get 1.06 10 to the power 8 hertz, which is 106 megahertz. So compare this to this. Can you see the huge difference? 1.106 megahertz, and this was 13.3 kilos. Okay, such a huge difference. What about the thermal noise? Do you expect it to be higher or lower than what we obtained for the high impedance? 2D? Yes, what did you say? Higher. And why it's higher? It's because, no, not RF, just smaller than R total. It's because we cannot keep increasing according to this, or why is this an advantage? Because we can keep the bandwidth large by increasing the G while keeping RF also large, which means that the noise will not be affected. The noise will not be increased. But due to stability issues, we will not be able to increase RF forever or to a very high value that will make the thermal noise of the transimpedance comparable to the thermal noise we get from the high impedance. Okay? And because we said this is the reason why we use the transimpedance for applications where we care about what there is two issues we need to achieve trade-off between the transimpedance and high impedance. High impedance was good with the thermal noise, and for the bandwidth we managed to compensate for that with equalization. But what was the limitation of the high impedance? No, that's not true, because it has low noise. And low noise means high sensitivity. The one that we cannot use for long haul applications is the low impedance, the very first one. Dynamic range. We said that it gets saturated. So the transimpedance is good for applications where we care more about the dynamic range, while the high impedance is used for applications where sensitivity is the most important for us and we don't really care about having a high dynamic range. Okay, so back to our question here. We want to calculate the thermal noise. So again, it will be, and we said that the thermal noise in this case is dominated by RF, and RF is much smaller than the R total. Okay? And if you do the calculations, you will find it 1.66 10 to the power minus 25 amperes squared per hertz. So compare this to this. So this was to the power minus 27, and this is to the power minus 25. And if you compare them, you will find that the thermal noise for the trans impedance is 20 times larger than the thermal noise of the high impedance, which is about 13 dP. So okay. So you can see the compromise between the bandwidth and getting rid of the equalization and the increase of the thermal noise. Is that clear?
Why do you use a bandwidth in the equation?
Because if you read the question, they want the thermal noise.
Is it per unit bandwidth?
Yes.
Yes. That is divided by 100.
So there was example. There were two examples from last time. One on the very last slide and one on one slide, two slides before that. The example saying on-off keying while implementation system. So what's wrong with this video? But let's try to do this until we get see what will happen with the computers today. There are copies here if you don't have a copy from last time. Keyboard. You don't have one? Can you share with him your laptop to keep a copy for myself and for this? So in the question they want us to determine the value of A1 that gives this error rate of 10 to the power minus 9. So what was the bit error rate according to last time? If you go one slide before, you will find that we agreed that the bit error rate is equal to half the complementary error function of A1 minus A0 over 2 sigma root 2. And what was A1? The one logic, and A0 is the amplitude of the zero logic. And what was the sigma? What was the sigma? From the Gaussian distribution. It's the variance of the Gaussian distribution.
Very.
And here the variance for us is what?
It's A1 minus A0.
Huh? The variance for us here is what? It's the noise. Do you remember? We said we have if this is A1,
Difference between A1
then we have a Gaussian distribution, A1. Okay, and we said this is because the accumulated noise from the different sources according to the central limit theorem will have a Gaussian distribution regardless of the distribution of each individual source. Okay, so using that, and given that the bit error rate is 10 to the power minus 9, we want to get A1. And they're telling us that no signal at 0 logic. So A0 is 0. Okay, and we have A0 equals 0. How do we get the complementary error function?
We made an assumption for it.
Yeah, we said that there is a good approximation of that, and where the complementary error function of x is given as 2e to the power minus x squared over x.
Yeah.
Okay. So for us here, we have half and if you solve for x, you will find that x is equal to 6 over root 2. Okay. And we said x is a1 over 2 sigma root 2, which will make a1 equals 12. What does that mean? When we say a1 is 12 the variance, what's the variance? No, not the variance. What is the meaning of the variance here?
It's the noise.
Noise. Okay, so this means that to get a bit error rate of 10 to the power minus 9, the power or the current at A1, logic 1, should be 12 times greater than the noise. Okay? And using that sigma is equal to 0.2 milliamps, then A1 is equal to 2.4 milliamps.
That's not fine.
Okay?
So will this approximation always be valid for us in this model?
Yes.
Okay.
If you remember, if you can see in
Yeah,
the sheet,
roughly.
say greater than 3, which is
Yeah.
true here.
For all our Exactly. No. Oh yeah. Save the boundary. You know the boundary.
So this was the example, and you remember last time we talked about responsivity. What was responsivity?
It was for the whole system.
Yes.
One second.
Oh, sorry. Should I write it again or be able to copy it from your colleague?
It's 2x times square root of pi, not 2x square root of x.
This one?
No, the blank of pi.
Here?
Yeah.
Sorry, this is.
There's a part.
Do it have a 2 here?
This one too. Sorry. I'm just using the function here.
Yeah.
So what was responsivity? This was just 2 days ago.
Yeah.
Remember?
Let's try to.
We said that responsivity and quantum efficiency, they basically describe the same thing, the same concept. While quantum efficiency was the rate of the generated electrons over the rate of received photons, the responsivity is given as
Amplitude over the power.
current,
Yeah.
to be more accurate, current over the power, the detector current over the incident optical power. That's why the responsivity is used to describe the whole system, the whole receiver, because it gives us values that we are related to the whole circuit, while quantum efficiency is used to describe the device, the detector itself, the efficiency of the detector. Okay, and that's why if you go back to the problems we solved before, where we were talking about the detector, we were using quantum efficiency. And the problem we will solve now, and we will see in other problems, where we talk about the whole receiver, we use responsivity. And responsivity is the detector current over the optical power, and the detector current can be given as the rate of the electrons multiplied by the electron charge, and the optical power is given as the rate of photons multiplied by the energy of a single photon, and these together are what?
Quantum efficiency.
Quantum efficiency. So that's why we can say responsivity is equal to quantum efficiency E over F. We have discussed all of that last week, so we are really efficient in using the time. Okay. In the example we just solved, we found that A1 is equal to 12 sigma. And this A1 is over logic 1 only. Logic 0 is 0 power. So the average power can be 6 sigma. Okay? And from here, the average power can be given as responsivity multiplied by the detector current. And we said this is noise. So the sigma can be given by summing all the noise sources we discussed before. The thermal, the shot noise, and so on. And if you remember, last time we discussed that to limit the noise, we use filtering. We use a filter, and it was found that a filter with a bandwidth of 0.7 the bit rate will give us a good approximation between reducing the noise and not introducing too much intersimple interference. Okay? So this sigma is given as the root of the mean square current of the noise. Okay. And we said that the current or the noise is filtered with a filter of 0.7 the bit rate. So then we can say that the sigma is equal to the noise or the root of the square mean square noise multiplied by the bandwidth of the filter, which will mean
No, it's faster. No, it's not 65, it's 6 sigma.
hmm?
Okay, yeah,
Mostly sample.
Sorry?
No, just
Yes. This is the total noise.
YP,
This is the bit rate.
I don't want to say
About
IR.
Yeah.
Is the power.
Yeah, R is the responsibility.
IRE.
Yes, here. Said the responsivity or the
I over
sorry. So the responsivity is the power or the so then so R
yeah. No.
so A1, sorry for that confusion. A1, this is current at logic 1. And we found that current at logic 1 is equal to 12 sigma,
Yeah.
12 times the noise. So the average will be 6 times the noise because the current at the logic 0 is 0. So we won't get the average, then it will be over 2. And the current here, I, according to this, is RP. So then RP is equal to 6 sigma, and sigma is the noise. Okay? So we can say that the power is equal to, we can get the I outside and keep here 0.7 multiplied by the bit rate.
So is that the average power?
Hmm?
The average power.
Average power.
I didn't get the part why A1 could be 12 sigma and it could be 6 sigma.
This is average.
Okay, like over a longer period. And
Because this is over the one only.
Okay.
Over 0, it's 0.
And the other one is like for the P, 12 sigma. So logic.
12 sigma is for logic 1. So we'll have something like this. For 0, it's 0. For 1, it's 12 sigma.
Yeah.
And you know we are assuming that ideal binary signaling where the number of zeros is, or the probability of 0 is equal to the probability of 1s. So then to get the average power, you can just divide by 2 because both of them, the zeros and the 1s, have the same probability. Is that clear? So then the average power is equal to I, the noise multiplied by 0.7, the bit rate, the root of 0.7 bit rate, divided by responsivity. And if we want it in dBm, we can get it. And here we have this example.
So you can't always compare.
Okay. So in this example, we have a transimpedance receiver dominated by thermal noise due to RF of 7.5 kilo ohms and responsivity of 0.7 amp per watt and a bit rate of 10 megabits per second. Then we can calculate the average power, as you can see. The point of this question that we want you to compare this to the limited detection example. You remember we solved this example in 2 lectures ago or something, and we found that the sensitivity or the minimum power at bit error rate of 10 to the power minus 9 was minus 76.9. Now it's minus 44.7. So why is this difference? What does this mean? What were we considering when we calculated the quantum limit? Well, I talked about that at the beginning of Tuesday lecture. Like, what is the difference between what we are doing now and what we did 2 weeks ago? In both cases, we were evaluating the performance of the system under noise. Here, we were obtaining or establishing the quantum limit, where we only consider the quantum noise. While here, what are we looking at? Are all the different, including thermal noise and shot noise. Okay, so that's why there is an increase in the average power. There, to achieve that bit error rate, we needed the minimum level of power was minus 76.9 dBm. Here it has raised to minus 44.7 dBm. Okay. Any questions before we go to the next topic?
So we're always looking for a smaller dBm. We're always looking for a smaller dBm.
Because this means that the receiver can receive or detect a very small signal, very small power. Minus. Okay, so we are done now with receivers. Today we'll look at optical amplifiers. If you remember in lecture 1, we said that the optical signal get attenuated as it travels through the optical fiber. And we will also see in the next sections that other optical components such as couplers and multiplexers will introduce some loss. Which means that after traveling a certain distance, the signal will get attenuated to the level that it is too weak to be detected. Before that happens, we need to restore the strength of the signal. The only option that was available initially was to do what? We discussed this. You had lots of questions about it in the first lecture. Regeneration. Regeneration was the only option to restore the strength of the signal. In regeneration, what happens in regeneration?
The signal will be amplified.
Regenerates the
The,
signal.
the noise. Amplify the noise. Amplify the noise.
What is the main characteristic of regeneration?
After.
The bad thing about regeneration. We discussed this in the first lecture.
It's active. It's active device.
The amplifiers are also active device. The optical amplifiers are also active devices. We said that in regeneration, we convert the signal from the optical domain to the electrical domain, shape it, clean it up, and convert it back to the optical and resend it again. So it's the optoelectronic conversion. This is the problem with regenerators. Regenerators were considered as one of the bottlenecks that are stopping us from exploiting the huge bandwidth potential of optical fiber. The other bottleneck is the electrical switching. Optical regenerators, as we said, involve the optoelectronic conversion, which means that we are limited by the speed of electronic circuits. To maintain or to speed up our system, we need to keep everything in the optical domain. In addition to that, regenerators are specific to the bitrate and format used. Means that every time we upgrade our system, we have to change the regenerator to go for a higher bitrate. Optical amplifiers came as an alternative that offers us many advantages over regenerators. First, they are insensitive to the bitrate and modulation format, which means that we can upgrade the system without changing the optical amplifiers. They first of all, they get rid of the optoelectronic converter. They do everything in the optical domain. And as we will see, they provide a large bandwidth, which means that they can amplify multiple wavelengths, which is an advantage for WDM systems. There are three main types of optical amplifiers: the erbium doped fiber amplifier, EDFA, the semiconductor optical amplifier, and the Raman amplifiers. The EDFAs have advantages over the other two types in terms of low noise, low insertion loss, and efficient pumping power. We will go through all these advantages. That's why EDFAs are the mainly used type of optical amplifiers, and we will concentrate or look only at them in this lecture. The technology of EDFA actually is quite mature now, and you'll find EDFAs in applications in systems like the transatlantic cable. The amplification in EDFA happens as a result of a combination of three processes: absorption, stimulated emission, and spontaneous emission. Before we look on how these three work together to give us amplification, we will look at each individually to understand how it works. We know from quantum physics that systems, for example atoms, they exist in a discrete number of energy levels. So if you consider these two energy levels, E2 and E1, where E2 is greater than E1, and we'll have atoms in E2, in E1, and atoms in E2. If we have an incident electromagnetic field whose wavelength is equivalent, or whose energy is equivalent to the energy difference between E2 and E1, this electromagnetic field will induce transitions between E1 and E2. Transitions can happen in the two directions, from E1 to E2, and in this case the atom will absorb a photon of the electromagnetic field, the incident electromagnetic field, to be able to go to the higher energy level. And also we can have transitions from E2 to E1. And in this case, the atom will fall down and it will emit a photon. This photon will have an energy, or it will be at the same wavelength. It will have the same energy and same wavelength of the incident photon. So okay, we refer to this as stimulated emission, to distinguish it from another type of emission that we'll discuss now. Okay, so if absorption dominates over emission, what will happen to the incident electromagnetic field? So the field, as it propagates, atoms at E1 will absorb photons to go to E2. So then what will happen to the field?
Be reduced.
Yes, attenuate.
Yeah.
So let's see here. If we have dominate over emission, what if emission dominate over absorption?
We'll have a population inversion.
This will happen later. But if we have more emission than absorption, so the electromagnetic field, as it propagates, it will stimulate photons or atoms at E2 to fall down to E1 and emit another photon. So what will happen here?
Amplification.
Amplification. So here.
Do you mean their attenuation, not absorption?
Ah, yes. Okay, quantum physics tells us that the transmission or the transmission rate between E2 to E1 is equal to the per atom is equal to the transmission rate between E1 to E2 per atom. What does that mean? So obviously we are interested in amplification. And if I can tell you that the probability that a photon here, an atom here will fall to A1 is the same as the probability of an atom here go up to E2. Then to achieve amplification, what do we need to achieve? This is what we were talking about.
Population inversion.
Yeah.
So having more emissions than absorptions.
No, yes, okay, we need to have more emission than absorption, we have agreed on that. But how to achieve that? Yes.
Do we add another level?
No. I think you have an idea about the whole thing, but it's not clear for you. We'll make it clear. Okay. If the rate is the same in the two directions, then to achieve amplification, we need to make sure that E2 has a higher population than E1. Okay, we need to have more photons here, more electrons here, atoms here than the atoms in E1. Okay? But at equilibrium, we know that systems, atoms here for us, tend to stay at the lower level. Which means that if we say this is N2, number population at level 2 and N1 population at level 1. At equilibrium, N1 is greater than N2, which is not what we really want. So 2. However, N1 is greater than N2. So we need to do something about that. This is what we call population inversion. Okay? So in population inversion, we pump the system with energy at a suitable form. So this energy can be absorbed by the atoms in E1 so that they can go up raised to E2. And by doing that, we make sure that N1 is, N2 is greater than N1. Okay? So now we understand the absorption, the stimulated emission. Actually, atoms will not stay at N2 forever, regardless or independent of any electromagnetic field applied. Atoms at E2 will spontaneously fall down to E1 and emit a photon. This photon will be, or will have the same energy as the incident, or any incident, whether it's the sub-incident power or not, but it will have an energy equal to the difference between the two levels of it. Okay, so keep this in mind. This phenomenon, we refer to it as spontaneous emission. So you can see the difference between spontaneous emission and stimulated emission. Stimulated emission happens as a result of an electromagnetic field inducing photons to go to a lower energy level and absorb and emit a photon, which will be at the same energy and same wavelength of the incident electromagnetic field, and it will be coherent also. Same propagation direction, same phase, and same polarization. Okay? So does everyone understand what we mean by the three? Absorption, stimulated emission, and spontaneous emission? Okay. Before we see how these three are put together to achieve amplification for us, let's first introduce ourselves to the EDFA structure. An EDFA, erbium doped fiber amplifier, is made of a liquid silica fiber whose core, or the core of that silica fiber, is doped with the rare earth element, ionized atoms of the rare earth element erbium. Okay, so it's a silica fiber. The core has erbium atoms, ionized atoms. The fiber is pumped with a pump signal from a laser. This signal is at a wavelength of, can be at a wavelength of 980 or 1480 nanometer. And you will see why shortly. And the pumping power is typically 100 milliwatts. One of the advantages we mentioned, now if you were paying attention, that the EDFA has low insertion loss. It can be spliced easily to the system with a loss of less than 0.2 dP. So, this is much lower than the loss for other amplifiers like the semiconductor optical amplifier. To merge or to join the input signal with the pump signal together, we use. Oh, you are not looking. Tell me. Okay, so you have your sheets. So, to input the two signals, the input signal and the pump signal to the fiber, we use a wavelength selective coupler. We'll study that component later. and also at the output to separate the amplified signal from any remaining signal from the pump. We'll also use a wavelength selective coupler. So this is basically the structure of the headphone.
What's this splice?
Splice is joining or inserting the amplifier into the system, into the whole fiber. So this insertion is called splicing, and it results in insertion loss. So for the EDFA, it's very low. Okay, so now we want to put everything together. Do you want to have a small break before we start this? Just 5 minutes. So now it's 4:58. We will come at 5:03.